Okay, let's get into seismic loads. They don't happen often, but when they do, they're extremely devastating. So we balance their infrequency with our design philosophy. And we'll see that as we get into it. Here's some steps on how we do it. So if you're unsure where to start here and just start working your way through it. We've talked about risk category in the previous vertical dead load stuff, or vertical loads, gravity loads. So let's start with finding the seismicity or the seismic parameters S sub 1 and S sub S. S sub S generally controls, but S sub 1 shows up in some important places. So we can use maps like this. We can zoom in on the Salt Lake Wasatch Front area, kind of peaks at 1.5 or 150%. You can see as you get down into LA, gets a lot higher. This can be nice, but actually using ATC Hazard website like this is really nice. So here in Orem we have 1.36. If we drag this up near downtown Salt Lake, what do we get? 1.53. And then if we drag this out to Long Beach, LA type area, Irvine I think is pretty high. You can see, oh, that drops down in Irvine. Let's see what here in LA is. So 1.9. Okay, so we can use that. It's a pretty effective tool, and that gives us some of our starting seismic parameters. So next we want to identify the site class. Ideally we get this from a geotech. If we don't have it and we know we're not on really poor soils, we can use site class D. That's the default. But ideally get it from the geotechnical engineer. From there, we have the F sub A and F sub V coefficients, which are based on site class and seismicity. So typically we're around here in Salt Lake. Site class D, we would be 1, which makes it convenient. And then 1.8 for the F sub V is kind of the corollary. And those play into these equations where we take the acceleration, the raw acceleration parameters, modify it for the site class, and we get SMS and SM1. For design, we take 2/3 of those. So SDS tends to be our dominant design parameter. And the first thing to note is we're reducing what we designed for by 1/3. So inherently, it's important to understand we're not ever designing for the full seismic force when we follow the traditional building codes. Risk category, or not risk, but seismic design category, will depend on what our SDS factors are. So if we're greater than 0.5, we'll be D. There's also a corollary to the S sub 1 factors, so SD1 may change things. Okay, sorry, I got distracted by a call there. So anyway, this risk category is important, or seismic design category is important because it feeds into the detailing requirements for certain building systems, like framing systems. And to understand that, we come to this table. So here we have different types of lateral systems. So we'll just say special reinforced concrete wall. It's no limit in B and C, but in seismic design category D through F, you can't go over 160 feet. It basically says the people that know the nuances of this don't believe the system's appropriate for taller buildings than 160. Some of the other factors are the R factor, which is fundamental to calculating the seismic force, the overstrength factor, and then the amplification factor for deflection. So just focusing on kind of a zoom in on that table, if an R of 5, you'll see here when we come to calculating the base shear, we're actually going to divide that into the SDS factor, which then multiplies by the weight to get the base shear. So if I have a building that I divide the seismic force by 5, that's big. That's a 5-fold reduction in force. The corollary to that is I have to then design that element to be ductile or to absorb energy. And so in a special reinforced concrete shear wall, I'm going to have to meet certain detailing requirements to make sure that wall behaves the way I expect it to, and I can justify reducing my seismic force by such a high number. Okay, so jumping more into this equation, base shear, which is the shear horizontal force at the base of the building, is the CS times W. What W is the weight. It's going to include some storage and snow loads of a certain magnitude. By and large, it's the dead load. And then the CS is a function of the SDS, which we've talked about, R, and the importance factor. All right, there's some other factors for the upper periods, and those are worth calculating and making sure we understand those. The next step that we get to is taking that base shear and distributing it up into the building. So at the base of the building, we say the base shear acts, but then let's take that force and distribute it upwards, and what you'll find is it's bigger the higher you get in the building based on this equation. So if we look at these two equations, the story force, so this could be F sub 1, F sub 2, F sub 3 is equal to the CVX, so CV1, CV2, CV3 in this case, times the base shear. The CV factor is a function of the weight of the story times its height from the base taken to the K factor, which is defined down here, and you guys can dig into that. That at a story is divided by the sum of WH to the K at each story, and what we find is that when we add these CVX's up, they add to 1. So here's an example that I've given you, and I calculated the CVX for this 3-story building. I add that up, it's 1. I multiply that by the base shear, I get these. That 66.5 equals the base shear in the building. So once we do that, then we can also take our force at the story and spread that out horizontally to each lateral element, shear wall, moment frame, brace frame, etc. Okay, so with that understood, now let's look at what E in the load combination means, and we'll look at load combos here in a minute. So E in the load combination has a EH, which is horizontal, and a vertical term. The vertical term is here, which is just a percentage of the dead load. The horizontal term is rho times QE. QE is what we're talking about from the base shear. It's this force, how it distributes through the building. We'll get way into that in the future. Times a redundancy factor. Ideally, rho should be 1 because that means our building is configured in a good way or in a high performing way. If we have lateral load steps or discontinuities in our lateral load path, this redundancy factor goes up, I think up to 3, but it's been a while since I've dug into it. Okay, I'm going to let you read those slides on your own. Load combos, basically we need to understand if we have dead, live, snow, wind, seismic, blast, soil loads, whatever, how do we add those together? And this table helps us do that. You'll notice there's 2 types. There's LRFD, which stands for load and resistance factor design, and there's allowable stress. So let's just look at these first 3. First 4. These are gravity load combinations. So here we have a live load heavy and a snow load heavy. The ASD has you mix live and snow in a certain way that's different than LRFD. We then have lateral load focus combinations, and there's 2 categories. One is just primary lateral loads, with heavy gravity loads, and then we have an overturning set where if the building's tipping over due to lateral forces and we're using the weight of the building to resist that, we want to use a minimized dead load or gravity load. So you'll notice in these overturning combos, there's no live or snow, just a lower percentage of dead load. And then jumping back to the lateral loads, we'll have dead, wind, live, and snow, and then seismic will have live and a portion of snow as well. Anyway, those combinations in software will expand quite a bit. Let me pull up what my standard combinations are, and you can see how those blossom or bloom into a design model. Okay, so here's my RAM elements template, and if I come here to load combinations, this would be for a more complex type project where there's material, there's conveyor belts, there's soil, there's ice loads. So these are my load cases, so single type of loads, and then the combinations are quite extensive that get built off of those. So everything above this point here are LRFD combos. Below that's allowable stress combos. It's easy just to set them both up so you get both fully calculated. So at the end of the day, what's important is I can go through a model, add in the loads for different types of things. So typical dead, equipment dead, material, this might be something in a bin, live loads, equipment live, etc. And then the software will combine those based on what the code requires. And because the code doesn't do the greatest job with industrial buildings, there's some things in here that are just kind of my interpretation and gut feel as to what the best practice would be. Okay, so that's load combos. Let's talk about drift. So drift is the relative story displacement between two floors. So if I'm on floor 50 of a building and 51, the drift between those two floors is what I want to look at, or any floor, but I want to limit it to a certain amount so I don't have too much damage to the building. So drift limits come from ASCE 7 or the building code. Different codes will have different values or similar values. But typically for your normal building, you're 0.025 or 0.02 times the story height. So basically 2% of the story height or 25 or 2.5% of the story height is what we want to limit the drift to. We calculate drift, so we calculate the limit, which is this delta A allowable. We calculate the actual drift from the model or by hand, and then we multiply it by this deflection amplification factor, C sub D, which accounts for the fact that we divided our seismic force by an R factor of a substantial value usually. So when I compare this table, I want to compare it to my actual calculated deflection times that amplification factor. All right, so you can see for different types of systems, and this is from a different table than what we've been looking at so far. I get my values there. All right, getting close to the end here. Let's see what else we have. Nothing. All right. So in summary, lateral loads, we want to pay really close attention to the load path, which basically can be a big element or a nail in a small connection. And then for seismic, we want to make sure we're creating a system that's ductile enough that it can absorb the energy. But I want to make it perfectly clear that we can design to the current seismic codes, have a major earthquake happen, and our building will be substantially damaged. The building code does not keep buildings after a seismic event in perfectly usable condition. It's a life safety code, which means if the building didn't fall down after an earthquake, the engineer did their job. Now, if you want to go to something more robust, you can go to performance-based design, and that provides more options, more design insight, but it also has a substantial increase in cost of the structural system. However, at the same time, that could really, to the cost of a project, only add 1 to 5% of the cost if you go to quite a high seismic performance level. But that's another day, another discussion for another day. All right, hopefully this gets you fired up on this stuff and we can talk more about it in class.